on to another weak chemical bond, and actually there's a mysterious chemical bond. Usually, even in the biology, the classroom, this chemical force is not the intention is missed out because it is a difficult concept to understand. However, however difficult it might be, it is actually the reality affecting seriously on the lives of all living organisms. So I have to mention and at least try to conceptually have a like closer, intimate feeling about this particular force. The name is a van der Waals force. It's kind of a mysterious, ambiguous attraction. It's a very temporary attraction. This is the momentary attraction occurring between two independent molecules. When those two independent molecules, their distance become close, like probably you maybe have a kind of similar occasions when two individuals get closer, you have a little bit of a kind of a subtle, strange attraction. But that's not that. I mean, this van der Waals force is not such kind of an emotional thing. So why, when these two molecules get near to each other, there are some more obvious force attraction is generated is the question. The reason is the random movement of these electrons on the orbital. So if you think about the one electrons moving on its own orbit, but actually if you trace down, and this electron's movement is not static but it's dynamic. So this movement at a random point, there might be some kind of the attraction. We call this a dipole, like opposite charge, partial charge, of course. So when here, on what occasion this particular end will become partially positively charged? When the electrons, let's for the sake of simplicity, let's think of this only one electron in this molecule. Whenever this electron moves far away from this end, and it will become temporarily and also very weakly, but it will become positively charged. Same thing. So the other end of this, the other molecule will have an chance of becoming partially negatively charged when electrons will arrive at this particular. And this is, as we can imagine, that this will be very, very short, instantaneous moment. But even that, at least instantaneously, they will have this attractive force generated. And think of that, this will just keep happening, being repeated. So overall, if you take the average, then you can just virtually say that there is an existing some force between these two, attraction force existing between these two molecules. That's what we call and what we understand as the van der Waals attractions. So the requirement for this van der Waals attraction is that they have to have some certain distance, very intimate distance. Like if they practice this social distancing, they will never have any van der Waals force generated. So if you have this very close, so that these two electrons moving around have a very, very slight kind of a having slight overlap, very, very slight overlap, then you have a very strong chance of having this van der Waals attraction. And if you go overboard, like too close, anytime you just go overboard, you will have a disaster. So they will have this, on the other hand, kind of opposite. The repelling force will be generated. So this to take advantage of this van der Waals attraction, you would have a very very well defined certain specific distance. And another important parameter affecting this van der Waals force is the area of contact. You can easily understand if these two areas are making this contact at the very pointed end versus if these two materials have a very larger contact area like this, and which one, even though these two molecules have the same molecular mass, but when you have this versus that, which one would have a higher chance of a stronger van der Waals force? Obviously this. So the contact area matters. And another thing is the shape. Not only the contact area, the larger contact area, however, if those two contact areas are kind of complementary, then you can have a much better the area contact, more stable. So this area itself and the geometry as in the form of a complementarity, these two parameters are very important in having good sound van der Waals interaction. So here actual experiment shows in proof is that although the very similar organic molecule having same carbon numbers and etc., so those two, like one having, when they have this very smaller contact area versus a larger contact area, then this temperature, the boiling point means the temperature, the energy required to put this thing away, so to destroy this, the van der Waals force. Obviously you can see in the data shows, so it's a much higher boiling point, which means it more difficult to separate them, which means they have a stronger, they were connected with stronger van der Waals force is the just case in point. Once again, it is an extremely weak chemical attraction, so even weaker than hydrogen bond. So why do we have to worry about this van der Waals force? Think of this way: antibody-antigen interaction. These days, nobody will just argue about against the importance of this antibody and antigen interaction in these days of the corona pandemic, and this is actually heavily dependent upon. I wouldn't say this the van der Waals force is the only force establishing, making possible this particular interaction, binding, but this is the major force. Surprise, surprise, surprise. This extremely weak force is the one actually making possible that the antibody antigen specific binding and interaction, right? And also enzyme substrate interaction, which is also extremely significant, and receptor ligand. Here, if some of you have a little bit of a confusion about hey, what's enzyme and substrate and what's the receptor ligand thing, then let me just reiterate this enzyme, same thing. Let's say this is an enzyme E, and there is some specific material specifically bind in certain area of the enzyme, which usually recognize the substrate. So that is a substrate and that is an enzyme. What happens if these two interaction goes? Then soon, very quickly, this substrate will become 2 or 3 or maybe 1 different product. So that's the chemical reaction catalyzed by the enzyme. So substrate will become the product by the action of enzyme catalysis. Very similar interaction between the receptor. Here there is a receptor. Receptor protein usually described as like this, like cup-like. And the material specifically recognized and bind, interact with this particular receptor is called ligand. So between this receptor and ligand interaction, this ligand could be, example is like hormone and many other biologically important substances. And these interactions are also like something that maintained by this van der Waals force is what it is saying. And all of these are very important, significant, critical. So here is actually molecular model illustrating the antibody antigen specific interactions in here, and some other molecules interactions are also shown in both the cases. These van der Waals interactions playing very significant role. And finally, very interesting another example is this the very cute peculiar lizard named gecko lizard. One among many other things, actually, this gecko lizard is renowned for their ability to being able to climb vertically climb up very clean surfaces like a glass wall. They can climb without any particular device or help. They can climb up just like as if they have some kind of suction installed at their foot, and that's how the actually photograph taken when they do this. And it turns out that reason why they can do this marvelous ability is the shape of the bottom of their feet. So if you just get a close look, and the structure of their feet at the bottom is highly folded and extended structures to be able to have a very enlarged surface contact area. Like to illustrate in using the diagram, if you zoom in each small area, it can go like so. You have really divided and then increasing, tremendously increasing this surface area of the contact. So with that, you can have like a momentous, instantaneous increase in the van der Waals interaction, and that's how they are able to climb up this very slippery and vertical glass wall-like surfaces. And also related with this van der Waals force is this so-called hydrophobic interactions. Basically what it is this hydrophobic interaction is it occurs in the aqueous, aqueous environment, which means simply the watery environment. The hydrophobic molecules have a problem of dealing with this watery environment, because the water molecule, individual water molecules are polar, and hydrophobic molecules don't have any kind of a conversation or contact with such nasty, outrageous individuals like water. Like water is a polar, which means they are hydrophilic. Water itself. I mean, no, we shouldn't actually put any judgment on the water itself, whether it's a hydrophilic or hydrophobic, because it's all regarding the relative terms with relation with the water. So let's leave water alone. Let's talk about relative the friendliness to the water. Yeah, so these non-polar molecules are Hydrophobic means they hate, they fear or hate contacting with the water because they are non-polar. Water is a polar on the other hand, so they don't have any kind of like a resemblance. They don't want to have anything, any business. So then all they try is, hey, how can I minimize? Is there any way I can actually avoid seeing that guy? That makes me like really really nervous, and even like, so I hate to seeing or making any contact with them. So they will naturally will clumped together, aggregate. So here the hydrophilic on the other hand, which is a polar. Hydrophilic molecules are polar. Having any charge or partial charge, like as you can see over here, this is a partially charged molecule. Have no problem of making any contact with the water because this area water will be partially negative, and this part of water which is coming from hydrogen will be partially positive, and this molecule itself has those certain area of partially positive and partially negative because of this polar. So polar molecules, either this partially charged molecule as well as ions, and all those polar molecules will have no problem of dealing with water, and they are collectively called hydrophilic. On the other hand, non-polar molecule like this, they don't have any. Just by looking at this molecular model, can you see why this molecule will be non-polar? Because you don't have any electronegative, like you see the hydrogen here, you see the carbon, right? So all of them have a very low electron negativity value, so they will have no polarity, so they will become non-polar, so will have any difficulty of interacting with this polar water molecule. So this non-polar molecule will become hydrophobic, which means water fearing or water hating. So the tendency is like in contrast to all these hydrophilic molecules love being associated with or being surrounded by the water molecule, these guys will love to stick together and then clump together so that at least they can minimize any of these surface area to themselves only, so that they can avoid any contact. That's the tendency. That kind of tendency is called hydrophobic interactions. This diagram will very well illustrate such thing. So each individual molecule will try to get into the area. However, if you do this shielding, so this area is something that having this hydrophobic interaction, at least this area can be saved. Okay. However, so a lot of people actually have this misconception about hydrophobic interaction in itself has any kind of a force, attraction force, like holding force. So hydrophobic interaction per se itself is not like holding force. Yeah, they can have this kind of clumping together, but can easily separate. However, luckily enough, there is another type of such interaction which may be able to save this hydrophobic interaction, which is what you know already that, which is the van der Waals interaction. As long as that contact area is complementary and large enough. So usually this hydrophobic interaction aided with the van der Waals force is now can play a very strong influence. It can have like a long-term long-lasting physical force, okay, in the watery environment. Okay, so this once you have this two surface area clumped together near approach, got closer together through the hydrophobic interaction. Now the van der Waals force accomplish this actual bond formation is. So that's the relationship. That's very close relationship between the hydrophobic interaction and the van der Waals force is the accurate way of describing this. And what's the importance of this hydrophobic interaction? Once again, is extremely important in determining the original native protein shape, protein structure, because proteins are also born in the watery environment, and proteins are like in nature, some area will have a polar hydrophilic area, whereas some other area particularly have the hydrophobic area. And in the water environment, this hydrophobic area will spontaneously will fold themselves to avoid any contact. And that folding, after the folding, that interaction can be maintained further by this van der Waals bond formation. So anyway, to begin with, this hydrophobic interaction is the first ever determining factor for any protein structure in this native watery environment. So I just pick up this diagram from internet. The quality of a figure is less than satisfactory, so sometime later I will have to redraw this thing myself on my own, but anyway, just with the time limitation, I just simply present as it is, but nonetheless it illustrates very well about the concept of this hydrophobic interaction. So in protein, when protein was first born, this is not a finished product, and the yellow area represent the any hydrophobic part, and around which initially at least, so this is this diagram is somewhat misleading in that all those water molecules are able to have like this intimate contact. No, that is not true. There will be a tremendous stress in terms of this energetics. So to avoid such a high degree of potential instability of in terms of the energy, that's why this hydrophobic area get together to have this aggregation, and so that this area can be protected from the water's surface area attack. So this is something that all happening spontaneously. Why? Because if you do this, then you will be able to lower the potential energy, which means the entropy. In terms of the entropy, you will increase the entropy. Whenever you have a consequence of increasing the entropy, that event will occur spontaneously on its own, okay, without trying to worry of spending any energy. And another very important feature about this hydrophobic interaction is oftentimes this incorrect shape of protein usually due to the mutation result in the incorrectly shaped proteins, and in the normal shape or structure of the protein, they don't have any this feature of clumping together aggregation. However, once you have this kind of a malformed protein, you have a much strong tendency of this having clumped together, affecting very, very serious negative impact in many different occasions. So here one example we can think of easily is the sickle cell anemia. um, which we are going to take a look at more, but in other chapters, because it bears many different relevance in different aspects of life science. But here, at least one thing you can notice the difference here is, look at the shape of this red blood cell, like this red blood cell versus normal red blood cell over here, is quite different. So this sickle shaped, crooked sickle shaped versus normal red blood cell, round donut, like unfinished donut like, or like a little bit slightly never mind, yeah, forget about that kind of weird example. But anyway, normally the red blood cell shape is quite different from that of the sickle shape. The red blood cell is because of actually the proteins, the hemoglobin protein, the hemoglobin protein produced in large number inside of the red blood cells is mainly responsible for the malformed red blood cell shape. Here, by the way, these are the white blood cells and other stuff in this photograph. I'm not really sure whether it's a really true photograph or simply computer generated image. I'm not really sure, but the point here is the normal hemoglobin molecule, each of which is carrying the function of transporting the oxygen, as we all know, have this particular shape. However, the mutated version of the sickle cell hemoglobin has a slightly different the structure, and due to that, this hydrophobic part has been exposed to the surface, and this exposed hydrophobic surface has a problem because they will try to avoid any contact with the water in this environment, and the way they can do is this: hide by connecting themselves together. And then that's the main reason why this the structurally incorrect form of hemoglobin clumped together to hide their exposed hydrophobic part through, what is this? This is another example of hydrophobic interaction, isn't it? And this is not the only example, this sickle cell anemia hemoglobin clumping together. In many other very significant serious pathological events, including diabetes and Parkinson's disease and even Alzheimer's, the main issue is that, like, associated with the protein aggregation, and most of these protein aggregations are like a consequence of this hydrophobic area clumping themselves to avoid the contact with water. Okay, so this as a final this is like actually not very important, some like I just throw the last minute extra gravy to have to ask you about this. What do you think? Because this, I found this figure in very renowned, famous biological textbook, indicating that this is an example of the hydrophobic interaction, like water, droplet of water having this very spherical shape on the surface of a plant. So I have an example, but this is another example of hydrophobic interactions. And no, hello, I don't care about how famous those authors are, or well-renowned biologists or whoever you are, but to me, it doesn't look like it's an example of hydrophobic interactions. Okay, for one thing, hydrophobic interaction should be what initiated by the hydrophobic part. Here, in this occasion, the surface, which is this surface is covered with like lipid waxy, so that's why they have a overall hydrophobic surface. On the platform of a hydrophobic surface, now this hydrophilic water molecule clumping together. That is not an example of hydrophobic interaction. Hello, sorry. This is only like due to some kind of a hydrogen bond interaction to minimize their energy status so that they can increase the entropy. So that's the best way possible to achieve the lowest status of energy. Not at all about consequence of this hydrophobic interaction, please. Okay. Okay. So with that, all the second part of the lecture was done. Once again, it's been way over 1 hour and 30 minutes, so I'm not really even sure whether I can be authorized to move on to the final part of this chapter, although I really would like to finish the last part of this lecture so that we can freshly start over the real biology in the next chapter in the next week. Let me think about it a little more so that I can just toss my burden onto you this week, or try to be more civilized instructor. Let me think for a moment. But for now, let me finish this part of the lecture with the intermediate summary, at least temporarily wishing you and having a very nice weekend. Okay? Min sista gnista hopp var att synas